So as I've been exploring the IMSAI 8080 emulator and front panel from the High Nibble, I've had to learn how to use the front panel. I've used a lot of front panels on machines, but not this particular one. I wanted to share some of those experiences with you, and the aim of this video, and it'll probably take a couple of them, is to get to the point where we can toggle in a simple program via the front panel and run it while creating enough context and understanding that you really understand why we're doing that. There may be a lot of content here that people already know. Just feel free to skip ahead. So anyhow, up on the Z80Pack website, I started to dig through the downloads here. I was really curious what was here. The High Nibble IMSAI 8080 is based on the Z80Pack. So as we go through the downloads, we find an IMSAI folder, and these are the files that the emulation is based on. And as I was looking through these, I found this little program called Light Demo. There's an assembly language source, there's a HEX file that's the output from the assembler, and there's a PRN file that would be what was sent to the printer. So I downloaded these to have a look at them, and in the assembly program here is the actual assembly code the programmer worked. And there's a couple of things to note here. The org statement says this code starts at address 0 in memory. It's got each one of the individual opcodes that create the code. So they're going to move immediate into the A register 01. They're going to rotate it right with carry. That's to set the carry bit, I believe, is what that's being done for. They're going to move immediate into the A register, the value FE hex. They're going to output that on port FF, or 255. Remember that the LEDs are inverted, meaning that where there's a 0 in this hex value, the LED will light. Where there's ones, it'll be off. There's a little delay loop that gets created right here. Really, it gets set up here. So the D register is loaded with a 1, the H register with a 0. And it loops here decrementing that value until it gets to no carry. So what's going to happen is it's going to say we don't have a carry bit set, jump back to the delay label, data it again, and just sit here and loop till the carry bit gets set, and then it'll actually went until the jump on no carry. I've got that backwards. The opcode here is jump on no carry. Once carry bit's cleared, it'll fall down. It'll do a rotate left through the carry bit of the value we loaded in A up here. It jumps up the loop, it outputs that to the LEDs, it does the delay, it rotates the bit. And what this does is just walk a single lit LED across that programmed output set of 8 LEDs, one lit LED at a time. The nice thing we have here is the printer output file, the PRN file, because what this gives us is a hexadecimal dump of what the program needs to look like in memory to execute. We've got those same opcodes over here. And these are the actual bytes that the assembler output. So again, the origin of the program is at address 0 in memory. At address 0, there's going to be a 3E. At address 1, oops, didn't mean to copy that, there's going to be a 01. Then we move on to address 2, where there's a 0F. And what's happening here is this instruction requires 2 bytes in memory. It requires the actual instruction, which is the 3E, and then it requires the data that it's going to work on, which is the 01. So this is going to be 2 entries in memory, address 0 and address 1. The rotate right carry, that's the hexadecimal value of the opcode. We're going to move FE hex into register A, so we have the opcode to do that, and we have the data. Move on to address 5. We're going to out on port 255, so we have the out instruction and the port number to write the A register out to. There's this LXI instruction that requires 3 bytes of memory, as shown here. There's another LXI that again requires 3 bytes of memory here. So notice that this is going address 7, address 8, oops, address 9, and then in hexadecimal we move to address A, which is this guy here, address B that gets these 2 bytes, address C that gets these 2 bytes, and then we come on to address D where it gets a 19. And remember, these are hexadecimal values, so one of the keys to being able to toggle this into the front panel is to understand enough about hexadecimal that you can convert that to the binary bit pattern that goes into the machine. And we'll jump into that in a little bit here, but giving this gave me what I needed to toggle that program in. So if we jump in here if I can find Excel, I've kind of created kind of a visual here of the front panel on my machine, where it's currently at. So what this represents is, in this case, this blue switch is down. All 16 of these switches are actually down. These switches, remember, are center off, so you can push them up or push them down. They're all in the center off position, and I have the power switch on. So the power switch has been put on. I've reset the machine by pushing up, and we're sitting here in a wait state. The machine's not running. We're looking at address 0. These LEDs are all off down here, and we can see the bit pattern that is in address 0. And if we jump back over to that hex listing, we'll see the value should be a 3E in hexadecimal. So the 3 is going to be represented in these 4 bits, and the E in these 4 bits down here. And if we look at this, I've got the decimal weight of these bits is written here, and it's on the front panel. If we take 8 and add 4, we get 9, 10, 11, 12. If we add 2 more, we get 14. If we do that in hex, we get 8 plus 4 is 8, 9, A, B, C, D, E, and we wanted an E written there. And so that's the bit pattern that represents that E in hexadecimal. The upper nibble of this, or the high nibble, where his kind of website comes from, was a 3. Was this right here was a 3. And if we look at this again, it is 2 plus 1, or that represents the 3. So we can see that I've already, in the first byte of the machine, loaded that bit pattern. Some notes here. We've got address 0 entered here. These switches are all down. We can click this switch up to examine, and we'll see up here that byte that lives in this address on the machine. If we push down to do an examine next, it would increment the address by 1. It would fetch that byte, and it would represent it up here. So this right here gives you the ability to set an address that you want to look at here on the front panel by setting switches up and down and do an examine and see the byte that's at that address. The deposit switch works in a similar way. Sitting here at address 0, I could toggle in whatever bit pattern I needed here and deposit, and that would deposit that bit pattern that's on these 8 switches here into that byte in memory. You'd see the bit pattern appear here at address 0. I could then toggle in the next bit pattern I wanted and do deposit next, and that would increment the address by 1 and deposit that 8-bit value into next. So really the way you work here is you reset it so you're at address 0. We've got the switches all at 0 as well. We toggle in the bit pattern here, so in this case it would be down, down, up, 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 down. We would do a deposit, and it would write this bit pattern based on the switch pattern into address 0. We could then come along and go on to the next byte, and the next byte in this case is 01. We would toggle in a 01 down here, so these switches would all be down, these 3 switches would be down, and this one would be up. And that would represent a 01 in hex, or in binary in this case, and we'd do a deposit next. That would increment the address and deposit that into the next address. So that's really the pattern we're going to use here. Is first byte gets deposited, the next byte is put into the switches and deposited next till we get all the switches, or all the bytes deposited in memory. The question then becomes kind of, well, how does hex and binary, how does this all map together? And apologies if you already have this clearly in your head. This is what I've created here. So we have the hex values here from F down to 0. If you were to count the unique set of switch combinations you would have, you discover there's 16 of them. So we have 0 to 15 unique patterns, or 16 total unique patterns. This represents one of the group of 4 switches on the front panel. So if I had a hex 0, all the switches are 0s. If I had a hex 1, I'm going to put a 1 in. If I had a hex 2, I'm going to put a 2 in. For a hex 3, I'm going to put in 2 plus 1 because it equals 3. And so up the chain. If we want to put in a hex 7, we're going to put in 4 plus 2 plus 1 is a 7. Switch 8 is down. And deposit that. And as we work our way up, this seems very logical. Get up to 9, and it's equal to 8 plus 1. A is just the hex representation for 10 in decimal. So 8 and 2 equals 10 in decimal. For a B, it's 11. 8 plus 2 plus 1 is 11. So what you need to get into your head is really this A through F in hex represent the decimal values 0 to 15 or these bit patterns. And however you choose to approach this, you just need to come up with a mental map so that when you say you see an E in the listing, you know to toggle an up, 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 down and deposit that. You'll need to play with this a bit if you haven't played with it. I've gotten fairly good at it. I got really good at it at one time. I've really kind of lost that. I haven't worked around assembly language for many, many years. But I know that A represents decimal 10, and so I'll toggle in 8, no 4, up, plus 2 gets me to 10, and no 1. And so I just toggle those in and I deposit it. If there's a C, I know 8 plus 4 is 12. C is equal to 12. 2 switches up, 2 switches down, and I've got the bit pattern. So really, that gets us to the point where hopefully, with some practice, you could look at a dump like this and read off the first byte, deposit it at this address. Read off the second byte, deposit it, the third byte, and deposit it, the fourth, the fifth, the sixth, till you got everything toggled into the machine. Once you've got these toggled into the machine, you can set all of these switches back down to 0 because we want to look at address 0. We can do either an examine, which would, that's probably the best bet. All the switches are down. We're going to try to examine address 0 as represented here. We're going to do an examine. We'll see these LEDs all go out. We're at address 0, and we would again see that, what was the pattern? 3E, 3 and E. We would see that pattern lit up here, and we would know, looking at the listing, that at address we should see a 3E. We could then do an examine next, click down here. This would switch to address 1, this LED would light, and we would expect a 001. And what we would hopefully see in the LEDs is everybody would be off except this guy down here is 01, and we could just do examine next, and walk our way through. If we got to a point where we made a mistake, where I'm looking at some address here and this pattern's wrong, I can set that pattern on the data switches here and deposit it to that location. So it gives you a method of entering the code, examining the code, correcting the code, and really the examine next and the deposit next will increment the address and then take you to the examine, read the byte or the deposit, write the byte into memory. When we're all done and happy with it, we can reset the machine to get back to address 0, and we can click run up. And run will go to address 0, fetch that byte out. In this case, it would fetch out the 3E here. It'll recognize that 3E bit pattern as the instruction move immediate A. Internally, it knows what that instruction is. It knows that instruction needs to go to address 1 to get the data, so it'll move on to address 1. It would fetch the byte 01, and it would load that into the A register. Then it would increment the address counter to address 2. It would read the 0F out of that memory location and know that was a rotate command, and so on and so forth. And then it would get into the delay loop here, and then the rotate left through carry, and jump back to loop. And something to notice here that might be a little confusing is the C3 is the jump instruction. The next byte is the lower byte in the address. So that really represents that byte right there. And the 00 represents the upper byte. So these are pure byte swap here. This jump is going to go to address 0005, which is what you see represented here. So you'll see the same thing here with this LXI instruction. Its data is a 1, and to represent a 1 in hex, go ahead and type it in here. That 1 in hex is going to look like 0001. Oops, 1. And what we're going to see here is the least significant byte up here and the most significant byte down here. That's just how the machine works. So this 1-1 is the LXID instruction. and it's going to load a 0001 into memory. So that's just something to keep in mind when you're toggling through and kind of looking at things about the byte order of these may not match what you would expect them to be. You'd expect to see address 0005 here. Well, it is address 0005. It's just they're byte swapped. You'll notice the same thing here on this instruction where it's just a jump if non-carry to address 000D, and there's where we have the 000D. So I think I've gotten through this pretty quick. Are there other things to really cover in this? I don't think so. Bit patterns in, reset the machine, run the program. What you'll see here is one lit LED walk across here, and then repeat the pattern. So it gives us something to play with. It gives us something to enter. So I think we'll move on here to actually bringing the machine up, looking at the actual physical front panel, and depositing that program into memory and running it. So obviously we're up on the bench, and I'm trying to get the camera set up here where we can see the full front panel. So let's go ahead and bring the system up. And we can see it came up as it should have. I'm going to go ahead and reset, even though it really won't make a difference. So what we're looking at here is we have address 0 on these LEDs, and the byte at that address is this 99. It just woke up with random garbage in memory. And what we want to do is toggle in this program. So the first thing we want to toggle in is a 3E. So that's 3, that's E. And I'm going to deposit this at address 0. So it's deposited. Then we want a 01. 01. And now I'm going to do a deposit next. So we're currently looking at address 0, but I want this deposited at address 1. So by pushing down here to deposit next, it deposited that 01 at address 0001. And we want to move on to a 0F, deposit next, and F. Actually, I did that wrong. Absolutely did that wrong. So at address 2, we need to input a 0F. I'm not sure what, oh, maybe I had that right. And let's deposit that at address 2. So we're looking at address 2. And we deposited a 0F. Okay, sorry, I'm kind of trying to think on too many things here. We want to deposit a 3E, which is that bit pattern, at address 3, and an FE at address 4. On to address 5 is a D3, 8, 9A, B, C, D, 3, deposit next, and then an FF, deposit next, and then a 1, 1, 1, 1, the next address, a 01 at the next address, and a 00 at the next address. And we're now looking at address 9. So we've got address 7, 8, and 9's got the 00. So far we're good. A 2, 1 at address A, 00 at address B and C, a 1, 9 at address D. So we're looking at address D, and we're going to want to deposit a 1, 9, and currently this is showing address B, 8, 9A, B, C. Yeah, C, I mean. So address B and then C. So the next address is going to be D, and we're going to deposit that 19. And we want a D2, 8, 9A, B, C, D, 2. Deposit next, 0D, 0, 8, 9A, B, C, D. Still struggling to get the hex fully encoded in my head. And then a 0, 0. Then a 0, 7. And then a C3, 8, 9A, B, C. And of course that's a 3. Deposit next. A 0, 5. Deposit next. And a 0, 0 deposit next. Now let's go ahead and reset, and we'll get back to address 0. And we can see we have a binary 3 on that side and a E on this side. So let's now go ahead and do an examine next. and we have a 0, 1, as we should have. This byte should be a 0F, a 3E, an FE, a D3, an FF, a 1, 1, a 0, 1, a 0, 0, a 2, 1, a 0, 0, a 0, 0, a 1, 9, a D2, a 0D, a 0, 0, 0, 7, C3, 0, 5, 0, 0. So it looks to me like we've got the program fully entered correctly. So let's go ahead and reset to get the address back at address 0. And now when I click run, it should start running that program. And obviously there's something wrong. It didn't do what I expected. So let's reset. Oh crud, I obviously had something wrong there because it's actually wiped memory out. This should have been a 3E and it's been overwritten with something. Even though we validated it. Deposit that address is 0. Okay, I'm confused here. Let's examine address is 0. Oh, it does have a 3E at address 0. Examine next. There's a 0, 2 there. And that was supposed to be a 0, 1, so let's deposit a 0, 1 there. Examine next. It's supposed to be a 0F. Deposit that there. I'm going to go ahead and reset and just examine what we've got so far. We've got a 3E, 0, 1, 0F. This is supposed to be a 3E, so we're going to deposit that here. An FE at the next address. B, C, D. Yep, that's a D. FF, deposit next. An FF, deposit next. A 1, 1, deposit next. A 0, 1, deposit next. A 0, 0, deposit next. A 2, 1, deposit next. Deposit next, deposit next. A 1, 9, deposit next. A D2, 8, 9A, B, C, D. D keeps confusing me. So we've got a D2. Going to go in at address E. Deposit next. A 0D. Deposit next. A 0, 0, deposit next. A 0, 7, deposit next. EC 7, C7, 8, 9A, B, C, and that's a 7. A 0, 5, deposit next, and a 0, 0, deposit next. Let's go ahead and examine addresses 0. We have the 3E, the 1, the 0F, the 3E, the FE. That was supposed to be a D3 here, and it's not. 8, 9, 8, B, C, D, 3. So I'm going to correct that, do a D3. Examine next, FF. Examine next, 1, 1, 0, 1, 0, 0, 2, 1, 0, 0, 0, 0, 1, 9, D2, 0D, 0, 0, 0, 7, C, that's supposed to be a C3. I'm going to deposit the C3 here. 8, 9, A, B, C, and of course 2 plus 1 is 3, so that's a C3. Let's examine the next address. It's a 0, 5, and a 0, 0. Let's go back and examine address 0 and just walk through it one more time. 3E, 0, 1, 0F, 3E, FE, D3, FF, 1, 1, 0, 1, 0, 0, 2, 1, 0, 0, 0, 0, 1, 9, D2, 0D, 0, 0, 07 C3 0500. So let's reset back to address 0 and run it again. There we go. So for whatever reason, the first time around, I had something wrong, and it actually overwrote itself, and we had to re-enter it. And this is what this program does: is it takes the programmed output, it shifts a single bit across to the left and displays it, and delays and displays it. So that's really what this little program does. We can stop the run here, and let's reset back to address 0. And we can single step through it. So we see the 3E. Let's run that instruction to the next address. There's the 01. Let's run the RRC command. We're now looking at a move immediate I. The A register, and the data we're going to move in is FE. We're going to output to FF the bit pattern. And as you saw, the bit pattern got written here, and the single bit showed up. Now, it would take a long time to step through the loop here. You can see it looping. We could be here. This is going to loop for a long time. So we really don't want to sit here for the next hour while I click this switch waiting for it to come out of the loop. But if we pick up running, it'll pick up and go again. So there it is. We've entered this series of bytes into memory twice, because the first time I did something wrong. Verified it, and we have it running. So there really is an example of entering a program into memory, into physical memory on the machine. Let's go ahead and stop. We'll talk a bit more about this. If I wanted to look at address 00FF, I'd input 00FF, and I'd do an examine. And there's something at that location. It's really power up garbage. And we could move on to address 0100. So if we do an examine next, we'll get a 0100. We can walk through memory up here. If we wanted to go directly to address E, we should find a D2. If we do an examine, we find a D2. So working with the machine, it's important. All 16 of these switches together are an address, and it says this here. You can also enter data on this lower 8 set here. So these switches serve double purpose. They can be used to set an address, or they can set data depending on what you do over here on the controls. This bank, as I think you've seen probably in a different video, can be read. So this is the output of port FF. And if we input from port FF, it would read these 8 switches. A port is like an external memory address. There's 256 ports available from 00 to FF. And rather than go to memory and do a fetch, it'll go to one of those 256 ports, and it'll either do a read from that port or a write. And ports are typically where you'll find things like UARTs, so you can talk to a serial terminal or maybe a printer interface. There's just all kinds of things. Ports are a way for the processor to talk to something external, either writing to it or reading from it. In this case, they've just designated port 255 in to be these switches and port 255 out to be those LEDs. You may notice up here that this LED is an import, and this LED would represent an out port. So let's go ahead and reset the machine and actually single step to the point where we would be doing an out port. So we're going to start single stepping through the instructions. Port address 4. We now see the D3, that's the out instruction. Now I don't know if we'll see it or not here. This out LED may blink when we actually do the out. There's the FF. There it is. So this instruction did an out port. It didn't, it actually latched. Did an out port to write that one up here on the LEDs, and we can see the machine and that instruction actually executed an out. And we can of course single step to the next instruction, and it's back doing memory reads. So So these LEDs here give you kind of an indication of what's going on the machine. In this case, it's reading from memory. This is, like I said, is input from a port, output from a port. And the other things here you can research on your own. They're a little too in-depth to get into here. But there it is. We've talked about hexadecimal. We've kind of talked about the overall control panel. We've looked at a live control panel. We've toggled in switches to enter a program. We've made a couple mistakes. We've corrected that program in place by using deposit switch up. So when we're at an address and the data is wrong, we put in the right data and we deposit over the top of what was there. We've used the deposit next to put in a byte and write it to the next address. We single-stepped a bit and looked at that kind of debug functionality. So I think we're covered here. I think that's really everything I wanted to hit in this video. So I guess I'll wrap it up here and we'll talk soon.